remember what it said. So, no, I can't answer that off the top of my head.
It's like, I missed like, long. I know she said, are you in your friend's fight? I said, no. She was like, why I ain't seen him? I said, well, Jake's got a job now. And she was like, well, I know Allison ain't got a job. And I said, well, Allison just be at home. Yes, hours, girls. Okay. All
right, so the note presentation we're going to use. All right, the note presentation I'm going to use. I did, I don't know, probably 5 years ago now, because the curriculum changed and they put something back in it. And y'all have heard me say before, I've gotten a little old and I tend to forget things. And so since I tend to forget things, I did this simply because I didn't want to forget some things. So I threw this together so that I would remember some things. So parts of it are very blank because I knew I would not forget these parts. And other parts of it are not, simply because I knew if I didn't write it down, I'd be like, oh, crap, and have sticky notes all over things or type it in the opening and remind myself, oh, yeah, I need to talk about that. So we're going to start quantum theory by talking about the wave particle nature of light. Now, this is going to go back quite a ways so that you understand why, well, I'm going to attempt to draw connections between why we're talking about what we are next week. Those of you who have a better middle school experience, how many of you remember frequency and wavelength from middle school? Okay, those of you who raised your hands. All right, today will be a little easier for you in parts of today's lecture. Those of you who went, are going to have to do a little more work studying for Monday's quiz than others of you. Yes, you have a quiz Monday.
Quiz.
Yes. Now, the wave particle nature of light. At one time, scientists, yep, it's going to sound like a story, believed that electrons behaved as particles. Now, when I say behaved as particles, I mean just like you would think they behave. Okay? Have mass, take up space. Okay? Now, light, scientists also believed that light behaved as waves. Now, if you have any recollection from middle school, you should remember that waves, okay, waves are energy. They have no mass at all. Energy has no mass. Does that sound even vaguely familiar from another science class?
Yeah.
Wait, which was them first? Like the ocean waves or land waves?
Which one was what?
First.
Well, technically, they're both the same in terms of being a wave.
Yeah, no, so which one came first? Which one was it? Called a wave first.
I have no earthly idea.
What wave are you talking about?
At the moment here, light waves.
In the Bible, it says that God made light first and then made everything else.
We can go with that if you would like. Okay?
When Molly brought in that Bible thing, I was like, okay, she been doing that. I was never known that.
Okay, moving on. So, scientists discovered that electrons can behave as both particles and waves. They have properties of both. All right. Now, all right, electrons can be both particles and waves. Now, back in, this would have been, I think, the 1800s, this would have been a very revolutionary idea, okay? For an electron to behave as a wave. Now, we're going to look at this. What's wrong?
What's that word? It had properties.
Yeah, had properties or have properties of both. Now, two examples that we're going to look at to illustrate this over the course of today and Monday. Okay, that we're going to look at to illustrate are neon lights and the photoelectric effect. Now, just to give you an idea of how the photoelectric effect works. The photoelectric effect is light shining on a metal and an electron is ejected. So, imagine that you have light. I can't fit that in there. It's too small. Okay, we'll get to it possibly today. All right, but light is going to shine down on a metal and an electron is going to be ejected. Now, usually if you want something to be ejected, you have to hit it with a hard object or something else, right? So if I have a set of tennis balls sitting there on the floor, can I shine light on them to get one of the tennis balls to move? No, I have to hit the tennis ball with some other object, right? It has to behave as a particle. I can hit it with a particle and get it to move. I can throw another tennis ball at it. I can throw a bowling ball at it. I can have Xavier walk over and kick it if I want to. Okay? Xavier can walk over with his... Okay, 13. So I was like, I got to estimate pretty big there. Okay?
Really loud and it wants to vibrate.
All right, it could vibrate enough, but odds are good it's probably not going to go very far.
Well, what if it like vibrates and it rolls off and then it keeps rolling?
Maybe.
It sounds
Okay.
so loud, like it's like thumping.
All right. Still, sound is a vibration which causes motion. Does light do that? No. Okay? But light could actually behave as a particle and cause something to move. Okay? Which was pretty revolutionary in the 1800s. So, if we're going to talk about that idea, we have to know something about waves. So, in order to do that, we need to study a little bit for a few minutes about what you know about waves, which is why we need to go back through this. Most of you had subs in middle school if we're looking at Tiffany's facial expression. So most of you just don't know a lot about waves. So let's go back and hit some highlights today and make sure everybody's on the same page. Okay, so for those of you who have a better background, I'm sorry that we have to go back and hit this. So what is electromagnetic radiation? Anybody ever heard of it before? All right.
Okay, it's got something to do with electricity and magnets and radiation.
Okay.
Y'all are geniuses.
It's any form of energy that travels through space in a wave-like behavior. Okay, the key being a form of energy. It has to travel through space. Okay. Has to be a form of energy. and it has to travel through space. Now, can any of you give me some examples of electromagnetic radiation? We're going to write those on the next board. I think I left space for it. Hold on one second. Yeah, I did. I thought I left space for it.
Light.
All right. First of all, if you want to abbreviate, you can abbreviate this as EMR. We often refer to it commonly as light as a shorthand, but it's really a misnomer. So, can you give me, why are you in here? Why are you going to acknowledge me? Just keep going. You're going to be back third period. Aren't you supposed to be doing something useful over there? Okay, I thought you might be learning something. We're supposed to be doing some kind of bum thing today. Okay, anyways, so, can you give me an example of a type of light that would work?
UV.
What?
I don't know.
What'd you say?
You said UV.
Yes. Does everybody have what they need here?
Yeah.
All right, so UV, for those of you who do not know, its full name is ultraviolet. Okay, ultraviolet. Can you give me another one?
Like, can animals? Wait, is there like some animals that can see?
Huh?
Are there some animals that can see that?
Yes. Some things have a different range that they can see. We cannot see ultraviolet light.
Wait. Is you? I ain't glad.
Where does ultraviolet light come from?
Sun.
The sun.
But don't
I'm just kidding.
they have like light bulbs? No. But we can see
Talking about a
the
black
sun.
light?
Yeah.
Yeah, but we can't see the UV light that comes from the sun. What kind of light can we see?
The sunlight. The heat.
It has a name.
What?
What it start with?
V.
Violet.
It starts with a V. Wait, a V.
Violet.
Oh.
That's a color.
Violet.
I'm trying to use the word.
That does not start with a V.
Don't talk about me.
Visual.
Okay.
Visible.
Visible.
The only one we can see is visible light. Okay? That's the only one we can see. Okay? So the violet color you yelled out falls in the range of visible light. Okay? What else can we see? Shh. That's good to know. Moving on. All right, give me something else we can see. Or can't see, because that's the only one we can see.
That's the only one we can see.
I know, so what else can't we see?
Oh, light.
Most of you probably have it in your house.
Hair.
Yes, we all have air. Thank goodness. Okay?
Oh my God.
So we have in our
house.
Huh? It's a type of electromagnetic radiation.
Give us a hint.
Huh?
Give us a hint.
I don't know.
Mine sits almost to the kitchen, but there's not quite enough space, so it sits at the edge of the dining room.
Chandelier.
That's on the ceiling.
Okay, wait, say it again.
A lamp.
No, the stove's in the kitchen, so is the refrigerator.
What'd you say? Say it again.
I need a type of electromagnetic radiation.
I'm talking about what you just said.
She said it's not in her dining room, but it's close to it because it can't fit in the dining room.
It can't fit in the kitchen, so it's in the dining
A
room.
heater.
Yeah, microwave rays.
Aren't you? Why? Isn't it bad for you to stand right there at the microwave?
Some research says yes, but a lot of it says no. I can't decide on that.
In Russia, are they outlawed?
Huh?
I thought they were outlawed in Russia.
Microwave?
They are.
You can't have microwaves in a restaurant?
In Russia.
Why are they outlawed in Russia?
Oh my
I don't know, that's what I
God.
All right, find your blue charts. We don't have all day. Find your blue charts.
Yes, I did.
Otherwise, I'm going to be here the rest of my natural life.
What are you looking for?
The blue tables.
Miss Laura, how you feel about people getting guns? How you feel about that?
Oh, no.
Me, I'm opposed.
You should.
Somebody was like they wouldn't want to make schools, but I would rather have it at these schools than a school like West. I don't know, I have
They've already had it.
I don't have a period
Already
to
had
50 and a whole bit.
We're all
Go to ISD.
We're not having that discussion. You asked, I answered, moving on. All right.
Well, if they come to a gun, I'm taking it.
Okay.
See,
Now.
people like that.
Exactly.
So if you look at the very bottom of the back page of your blue chart, back page of your blue chart, guys, and some of y'all are searching for the page, back page. All right. Now, do you see the electromagnetic spectrum?
Yeah.
See anything that looks familiar? Okay.
The bottom.
Okay, the visible light is the one that I said we see. So those of you who yelled out like violet a minute ago, that's one of the colors that we see in the visible spectrum. We'll talk about that after a while. Now, visible light is that itty bitty band, that little itty bitty band that we can see. Everything else needs to be up there. We have UV and microwaves. So what else is on that spectrum that's a type of EMR? Gamma rays. Gamma rays,
Radio waves.
X-rays, I heard radio, infrared.
Heat waves.
What I missed?
That's
What
it.
did you say, Zoe?
Okay. Now, okay, all of those are types of electromagnetic radiation. The only section that we see, though, is visible. We can't see microwaves. We can't see UV. If we could, all those dumb white people who sit out every summer turning themselves brown would get out of the way so we don't get skin cancer. But instead, we still slather ourselves up with oil and try to get darker every summer. Okay? Now, can't fix it.
You burn Miss Ball. You look
like
you
you
burn.
Now I do. I didn't when I was younger. Now I have enough sense not to sit out there. Everybody have it.
No.
It's like a
Is it true that after 18 our skin is like?
It's on the back of this.
I have no idea. Miss Thornhill can probably tell you. Now, what are the two properties that identify the EMR? How do we decide if you're a microwave? How do we decide if you're a UV light and we can see you? Or if you're a gamma ray, which is going to cause cancer? So what's the length of the wave called?
longer and shorter.
It's got a name. What's the change the length of the wave into a word? Wavelength.
Wavelength.
Okay. So wavelength. And this one's not on your paper. You might remember this other one from middle school maybe or another science class. Starts with an F. I'll give you a hint. You might use it to tune in your radio.
FM.
FM.
What's the F stand for? FM.
Finette. No, that's.
Frequency.
Yes. You know, some days I'm amazed. I'm just amazed at how much y'all science background has been stunted.
Yeah, you see, science and math are like, the teachers suck all the time.
All right, I need to see what I got. Okay.
Frequency and what?
Frequency and wavelength. Now, I've got a slide for each of those so you don't need to leave space.
We don't need to leave space for
No, I've got a slide for them. That's what I was just checking. All right, does everybody have it? All right, so this was on your blue sheet, right? So what is that electromagnetic spectrum? You don't have to draw the chart. You just need to know what the spectrum is called. All right, what is the electromagnetic spectrum? What does it do? What does this handy dandy thing right here on your blue sheet do for you?
Measures,
The length.
waves.
It shows all types of EMR arranged. I want too many R's here. By, all right, shows all types of EMR arranged by, what is this stuff arranged by?
Wavelength.
Wavelength. Now, if I should ask you, which of the following has the longest wavelength? And I give you 4 choices. Does everybody see these lovely arrows on their EMR chart? Okay? Because you may have to read that. Will I say in the question? Look at your blue chart.
No.
Because I didn't say that on the benchmark. You just had to know to find specific heat, right? And some of us didn't find the specific heat, did we?
Nope.
I won't do it on the test either. Okay? So if I say which of the following has the longest wavelength, you're going to have to know, oh, it was on that blue chart. I got to look there. And so all I have to do is look to see where these things are. Who has the shortest wavelength? Gamma has the shortest wavelength. Who has the longest wavelength? Radio. Now, if I said, who is also a radio wave, which type of wave is also a radio wave? Microwave. See how microwave overlays radio? Okay, a microwave is technically a type of radio wave. Okay, see how they overlay each other? So you could read that off the chart. So an ultraviolet is also like an X-ray. Yes.
What about
So
infrared?
Now, notice that gamma and X-ray overlay one another, which is why when you go for X-rays, if you are in a dentist office, what do they put on you when you have X-rays? They put a lead vest on you because they're just X-raying your teeth. Do your internal organs need to be exposed to the X-rays? No. Okay? Now, they have determined that, yes, your teeth need to be X-rays. Your brain might be exposed to a little bit of radiation. However, it's more important to see your teeth than worry about your brain. But this doesn't, you're not going to be exposed to it for great, you're not going to die. You're not going to be exposed to tremendous amounts of radiation. Moving on. Now, what is wavelength? Now, what definition will I not take on Monday? The length of a wave. If you write that down, you're not getting any points. Okay? Let's just be clear about that today. All right? A wavelength is the distance between. I can't fix that for you. The distance between two corresponding points on adjacent waves. Okay. Right? Yep. Points. PTS. Points.
Do we need to draw the?
Yes, because we're going to label it. You got to be able to draw it and find it. All right. The distance between points on adjacent waves.
We're gonna have to draw it on a quiz.
Possibly.
How about let's make that possibly a no.
All right. So when you draw waves, this is not necessarily something that you have to do for me because my course is about wavelength and frequency, but you should know that this is called a what? Anybody remember? This bottom part of the wave is called a trough.
Trough.
Oh, I remember.
And this very top part is called a crest. Okay?
Trough.
Now, I will not ask you those words because that's not technically part of my curriculum. However, you should be able to refer to that as a crest or trough. Only because I will refer to it that way. No. Now, distance between two corresponding points. Now, a wavelength does not necessarily have to be from the same point every single time. It has to have a corresponding point, and they have to be adjacent waves. What does adjacent mean in math class? Beside each other. So let's say that we take this wave and this wave because they're beside each other, right? If I choose to take the crest on this wave, I have to choose the what on this wave? The crest, because I pick the crest on this wave, I go to the crest on this wave. I have to pick the same points on the wave that's side by side. So since I picked the crest here, I have to pick the crest there. Does that make sense? Okay. So on this wave, suppose I said I'm picking the trough. What do I go to on the next wave? The trough. Okay? It doesn't have to be always the crest. Does that make sense? So if I, again, said I'm going to pick this point right here where I'm going down on this wave. I again go to the same point going down on the next wave. That would be a wavelength. Does that make sense? Got to go straight across. Now, the unit for wavelength, because this is the one thing we're going to calculate in this whole next 4 weeks, is going to be a meter or a nanometer. So we will have M or NM. Now, the symbol that we will use is an upside down Y, which is known as lambda. It's a Greek letter. If you're familiar with the Greek alphabet, it's one of the Greek letters in the Greek alphabet.
You said
Is that LAM?
B-D-A, like lamb, like bat, sheep, and then put D-A on the end.
Lambda. I thought it was Lambda.
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 All right, everybody got it? All right, now we got to do frequency. All right, frequency. Frequency is a time. All right, frequency is the number of waves that pass a given point in a given time. It's the number of waves that pass a given point in a given time.
What is that? Genetic?
Huh?
What is that?
In a given time? Where are you at?
Giving you their passport.
That pass a given point in a given time. All right, so when we want to find frequency, frequency is what? What's on top? So number of waves over the what? Over the time. Now, what makes up a wave? You got to know that piece to be able to count the waves. What makes up a wave? A crest and a what? There you go. Okay, so one wave equals a crest and a trough. So when I draw my waves, and I have done this for all the waves I've illustrated for y'all, if I have 3 crests, how many troughs do I have? I have 3. Okay, so this right here is one wave. Does that make sense?
Yeah.
Okay. So when I go to calculate up here, all right, I need to calculate my waves. So my frequency is, how many waves do I have? If you have the same crests as troughs, all you need to count are the crests.
3.
I got 3 over, what's my time? 1. So I get 3. Now, my unit for frequency is a hertz, H-E-R-T-Z. It's abbreviated Hz. And it has a definition. It's 1 cycle per second. And its symbol is the Greek letter nu, and it's essentially a V. Now, I'm supposed to italicize the V, but I have no way to italicize that writing up here on the board. So when I have it on the test, I can italicize the V when I type, but do I have any way to make this V italicized? I have tried that for years, Andy. It just looks jacked up. Okay, I cannot italicize a V.
Is that H or Z?
It's supposed to here. That's HZ. Just an ugly Z.
That's a one cycle for thing.
Uh-huh. Yep. All right, we caught up. Need to wait. Where are we at? All right, so higher frequency and wavelength related to each other. Anybody know?
They both do it with.
Mm-hmm. All right. What's that mean? All right, it's a math term. Tell me what that means. So what inversely proportional means? It's a math word.
They're opposites.
Okay, so
Are the same?
They equal.
Or they're
okay, they're opposites. So go with that. What's their opposites mean in math class?
They're like
That is
opposites.
Okay, hold on. This is what you're trying to tell me.
Like if one of them is like 2, the other one is like I don't know. Alright, so inverse is like
Okay, they're flipped. It's not a bad answer. So if one goes up, the other goes.
down. Sideways.
All right. But if one quantity increases, the other decreases. Okay? If one quantity increases, the other decreases. So later, we're going to talk about directly proportional. What does directly proportional mean? If one goes up, the other goes up. That means they both go the same direction. Nothing goes sideways.
Wavelength.
I'm less fried.
I don't know.
Man, if you have a clock,
All right. Everybody caught up? Can I turn back? Because I need to go back several slides. All right. So, whoops, too far. All right. So if we go back to your picture, well, let me fix that. All right. To here. Now, you just said they're opposites of each other, right? So this said long wavelength, short wavelength. What's that mean, though, if they're opposites of each other? How are we going to use that information?
Like a certain amount of gammas can equal like one radio wave.
Short wavelength.
Is that what a
Short wavelength has like higher frequency.
Okay. If you have a short wavelength, don't write this on your chart. This means you have a high frequency. We're going to add this to your notes in just a second. Okay? And if you have a long wavelength, this means you have a low frequency. Okay? Now, you cannot write this on your blue chart, but we're going to add this to your notes in just a minute. Okay? But that's what you have to translate in your head from that relationship. Okay? Does that make sense? That's why we're learning the relationship. Yes? No? Huh?
Why can't we write on ourselves?
Because you can't. You got to know it.
Could be on the quiz on one day.
Is this going to be? No, I wouldn't put this on the quiz Monday. Not yet, anyways. I will eventually, but not Monday. All right. Let's see what I have there. Not yet. All right. So, if we look at what you know, all right, let's say that we have a wave, because some of you don't understand what that means. If we have something like this, and we have something like this. Tell me what the difference is between this wave and this wave.
The one on the.
What can you tell me about this one and its number of waves? Okay. This one has a large number of waves. Okay. Does everybody understand that that's what we mean by high frequency?
More waves.
Okay. I just sort of assumed that when y'all say high frequency, that you guys understand that's what we mean. Am I jumping to conclusions when I leap there? Or is everybody with me on that? Okay. This is a high frequency wave because there's a large number of waves. If we actually counted them, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So there's 9 actual waves here. If I put a time there and wrote 1 second at the end so we could have an actual frequency, we could say is 9 hertz. Okay. Now, if I look at this bottom one I drew, okay, what can you tell me? Okay, it has a small number of waves. Okay, small number of waves. So this would be a small frequency. Okay, so we'd only have 3 waves here, which would be 3 hertz. Okay, because we're going to assume 1 second again. You can change the time to anything you want, but I always use 1 second because it's easy on my mouth. So, how does that affect wavelength? They're opposites of each other, right? So, if I have a high frequency, what does that do to wavelength? That's right. So, high frequency equals low wavelength. All right, so look at the 2 words we used. We used high and low. If I look at, all right, low frequency here, what can you tell me about this wavelength? Okay, it's a long wavelength. Look at the 2 words you used this time. Low and long. Are they the same or are they opposites? They're opposites of each other. Okay? That's the point that I'm trying to make. Do you see that, or am I the only one in the room who sees that?
We see it.
You sure? Okay. I just want you to understand. So on your chart where it says, okay, all right, I think it was this way. Said what? Small wavelength, short wavelength. How'd they have it labeled?
Short.
Short. I want to use the same. I want to use the same language. Okay. And then they had long wavelength, right? It's up to you. So on your table where they have it labeled that way, right? What do you know? Where it says short wavelength, you know what? High frequency. And where it says long wavelength, you have to know what? Low frequency. So if on the test, and I wouldn't ask this Monday, but I would later in the week, maybe Tuesday or Wednesday. If I gave you, say, 4 choices, and I said, who has the lowest frequency, I would expect you to be able to pick out of the 4 choices, who has the lowest frequency. Now, if you just look at the table right now, you would be able to say who has the lowest frequency. Radio waves. But if radio waves is not listed, Who's the next lowest frequency if you don't use radio waves? Microwaves. Okay? Any questions about how to do that?
Why is it called microwave?
Truthfully, I have no idea. You can research that and find out, but I have no idea. It's not an interest I have. No idea. All right, so here's the math portion of the day. Last math equation we're doing for about 4 weeks. C, let me change my color.
Oh, man.
C equals lambda nu. I have to think about it because in physical science we don't use the same letters for the same equation. All right, C equals lambda nu. I changed the letters in physical science for some stupid reason. So I got to make sure I use the right ones in here. All right, so C. Anybody recognize that letter from another math equation or formula in science that maybe you learned in elementary or middle school? Nope. Maybe if you did a report on some scientist, maybe for some extra credit?
No.
E equals mc squared?
Oh, sure.
Einstein. Okay, the C stands for the speed of light. And it is a constant. You have to memorize it. It is not on your reference table. This formula is not on your reference table. Remember, you're in an honors class. There's extras y'all have to do. Some of this in this unit is extra. A lot of this unit is part of your extra. Now, we just said that lambda is what? What unit did we say lambda went with? Try again. That was your wavelength. All right, and it has to be in meters. And the V or the nu is frequency. And it has to be in hertz. Okay? Those are the units they have to be in. Questions about what the letters stand for, what units they have to be in. This one's a constant. Now, you should remember from math class, constants never change. You just plug them in where they go.
How many meters per second is that?
Times 10 to the 8th.
How many?
Oh, that would be 300 million in 1 second. So that's 300 million meter sticks in 1 second. One tick on the clock.
So so when scientists talk about planets being light years away, that's like how much light travels in a year, right?
Ooh.
Dang.
Yep.
For real, what you say?
He said, when scientists talk about planets being light years away, it's like light in a year.
How many seconds are in a year?
And that's how many seconds.
That's how many meters in 1 second.
And do that times, yeah.
Okay? That's one tick on the clock. Okay? That's how many meters light travels in 1 tick on the clock. All right. All right. Here's a typical problem you'll be asked to do.
My mom's not here today. I'm gonna go home.
We're all ready to go home. It's Friday.
So what is it?
However,
What is V?
V is frequency. It has to be in hertz.
What is it? What isn't it?
It's actually F in physical science, but in chemistry we use Greek letters for everything.
Okay.
All right, so we're going to figure out the color and the frequency of light that has a wavelength of 450 nanometers. Dang, child was attacked by a coyote in Davie County.
What? You got coyotes?
We got coyotes here.
I saw a picture of how many coyotes can use.
That was a
You
fox
said what? You said
near
in
my
Davie County?
Davie County.
Are foxes dangerous?
Can be. Can be a rabbit.
I like fox.
She gets my dog.
You won't. Bro, you
I don't
don't
get
want
my
to
dog.
box.
I was killed. Right, Chanel gets on my nerves, but I ain't gonna let her fox.
You gonna run out
Yeah,
there?
y'all need to get rid of it.
I need to get rid of it. Did you not hear?
Wait, we had coyotes go? What she said?
She said, what are you gonna do when out there? I'm gonna shoot it.
Oh, really?
And I'm gonna put pelt on my floor and carpet.
Who gun you
Or
want?
they-
I don't know, somebody. I'm gonna get licensed.
First, she's gonna run around the neighborhood to find a gun. Then she's gonna tell the fox, stand still while I go
I'm
get a gun.
like, hey, hey. And then she's gonna go and she's like, stay right there.
All right, so what do we have to do? What do you think?
Well, we gotta have our equation.
All right, so we know we need C equals lambda nu.
Yeah.
All right, and we know C is equal to what?
Speed of light.
The speed of light.
3.0.
Times 10 to the 8 meters over seconds. So we need wavelength and we need frequency. All right, we're finding what? So we're looking for that. So we need wavelength. Now, this is in what unit? Nanometers. It needs to match meters, right? So we got to convert it. Here's a new conversion factor for you to know
Great.
because you don't have enough. 1 meter is equal to 1 times 10 to the 9th nanometers.
Great.
What do the 2 zeros beside the 3 and
So a billion?
speed do?
Other than significant digits, nothing.
That's a billion, right?
Oh, we're gonna have to have significant the digits in.
Yeah,
That's a billion?
I think so. I didn't expand it out, but I think so.
Okay. Because with the 8, it was 300,000, so that'd be a billion.
That's-
No,
I don't know. Expand it out.
How do you type that little 2 thing?
All right, so 450 nanometers. What goes on the bottom of our chart?
Nanometers?
What goes on top?
Meters?
Who's,
Meters is bigger.
I mean, nanometers.
Hold on.
The
Just
one
gave it to you.
times
1 times 10 to the,
nice.
the reason I gave it to you is it in the King Henry died by drinking chocolate milk? No, nanometers is significantly lower than milli. So, punching it in your calculator,
4.5.
all right, 4.5 times 10 to the negative 7th. The important piece in this is that it is now in what unit? Meters. Now, our units do what? They match. Now we can solve. Now, we have all the information we need, A, to find frequency, but more importantly, we also have the information we need to find color. Let me check, see if I actually plugged in the chart. Yes, I'm so smart some days. All right. Does everybody have what they need? All right, well, hang on for a second. So, we need to find color, right? Got your blue table?
Yeah.
All right, find your blue table if you don't have it out and handy. So, color, the only place we can find color is in the visible spectrum, correct? Because we can't see microwaves, radio waves, infrared, can't see any of that crap. They don't have colors because we can't see colors there. So, looking at your visible spectrum, we just found the wavelength, right? So we're going to find the color using this wavelength. So, 4.5 times 10 to the negative 7th. This is a number line, right? Where does 4.5 fit on the number line? Does it fit between 4.0 and 4.2? Does it fit between 4.2 and 4.9?
Yes.
I love when people tell me no. All right. 4.5 fits between 4.2 and 4.9. So the color is what? It is blue. Okay. So the color is blue.
So when you have like different colors, does it separate even smaller?
It can be a shade, yes, but I won't give you anything that's a shade.
So you're
So what?
saying that, like, what makes colors?
There's a whole bunch of things with reflected, absorb, and all the rest of that, yes, but we're not going there today. Yes, it's based on the wavelength. Okay? Now, so the last piece we need is frequency, right? So at this point, you just need to plug and chug the way you've always learned in math class. So C is 3.00 times 10 to the 8th equals wavelength is 4.5 times 10 to the 7th, negative 7th, times V. So to get V by itself, we're doing what? We're dividing. And then calculate. Oops, negative looks a little terrible there.
It's 6.67 times 10.
6.67 times 10 to the 14th. What unit do I put on a frequency?
Hertz.
Hertz. Questions?
Wait, is that a 16 or a 14?
It's a 14. I erased it, tried to make it look better.
I thought it was 6.
Hey, I tried to make it look better.
It's 16.
What's the 16?
Oh, it's a 14?
It's a 14. I already erased it, tried to make it look better.
I thought it was a 14 at first, and then I was like, oh, that's a 16. So I erased it. Good job.
Yeah, she's gonna get y'all over.
So how did you do that last step again?
You mean where I divided?
Yeah.
The variable has that number on it, so I divided by it to make it cancel. And I divided here by the same number.
What?
Really?
I'm sorry.
Is this number equals this number times V, right? I need this number off the V, so I just divided by it and made it cancel out. So if I divided this number by that, I have to divide this number by that same number, right?
Yeah.
Okay.
So I thought it was.
Oh. All right.
She said no.
Y'all do that one. Quickly. Yes, I am.
Wow.
We done?
Yes.
All right, so what color did we decide it was?
Orange.
All right, so when you did this, you got 6.25 times 10 to the negative 7 meters. So you look back over here and you said 6.25 puts us here and got orange. Yes?
Yep.
Everybody okay with that or no? Anybody not okay with how we got 6.25 times 10 to the negative 7? Yeah? Okay. So you take the 625 nanometers to meters. Who's bigger? Meters, so we put a 1, and then the nanometers is the 1 times 10 to the 9th. Okay? So 1 times 10 to the 9th. And when you plug that in, that's where I got the 6.25 times 10 to the negative 7 meters. Does that make sense, Justice? Okay. So that's how I got that and got orange for the color. Okay, so from there, I said C equals lambda nu. C is what? 3 times 10 to the 8 meters per second. And I'm going to take that off just so it's not in the way of calculating. And then my wavelength is 6.25 times 10 to the negative 7th, and then times V. So to get V, I do what? I divide by 6.25 times 10 to the negative 7th, and 6.25 times 10 to the negative 7th. Somebody tell me what y'all got for that. 4.8 times 10 to the 14th and hertz. Questions? Anybody? Does that help?
Yeah.
I wasn't talking to y'all. I'm talking to Justice.
Not really. Oh, that did, but I already know.
You already know what?
I'm gonna forget.
You're going to forget. Practice this weekend. On the homework, there's another one.
Might as well get some homework now.
I'm not giving you homework now. All right. So, what is the photoelectric effect? I told you we'd get to it before we got out of here today. Now, the reason we talked about the dual wave and all this crap we've just been practicing is to get to the photoelectric effect. So electrons can behave as waves. Well, where do we see examples of that? The 2 examples I told you we were going to talk about are neon light, which we will not get to until next Monday. We're going to get a little bit of a heads up about the photoelectric effect. We're not going to get very far. We're just going to start it. So what is this photoelectric effect that I speak of? All right. This is the emission of electrons from a metal when light shines on it. Okay. So in your mind, I want you to think of a piece of aluminum foil stretched out on the kitchen counter. Okay? Piece of foil. You got some light shining down on it. And an electron pops off. Okay? That's what I want you to envision from that definition. Okay? Light is being shined down onto a metal, and an electron is ejected from that metal. Now, it doesn't have to be aluminum foil. It could be a piece of steel. It could be a piece of copper. It could be any kind of metal. But it is a piece of metal, and the electron is ejected or emitted from the metal. Now, does that concept seem bizarre to y'all? It seems bizarre to me too. Okay? Now, just like we talked about earlier with the tennis balls, this was a revolutionary concept in the late 1800s, early 1900s. So, now, the mystery of the photoelectric effect involves the frequency of light. So this is what we're going to talk about next week. This is going to be the big thinking that we're going to talk about on Monday. What on earth is causing this electron to be ejected from the metal? Okay? How does this work? Why does it work that way? The mystery of the photoelectric effect involves the frequency of the light striking the metal. Can the frequency of light be any frequency? Does it have to be a high frequency? Can it be a low frequency? Doesn't matter. What do you think?
I don't know.
It don't matter.
It don't matter. So we could just use the light bulbs in here.
No.
We just have some aluminum foil on the desktop in here, shine some light down, and electrons are going to just jump out of the aluminum foil and be given off to the atmosphere. You think that works? No, it doesn't. Okay? Yeah, it would be cool, but it doesn't work that way. Okay? Now, current wave theory at that time. Okay? Current wave theory predicted that that's exactly what would happen. Any frequency would eject an electron. Any light, this light. And you all have cool lava lamps or any other kind of cool lamps in your bedroom? Those kind of lights would eject an electron from some aluminum foil. But in all reality, that does not work. So there has to be some explanation out there for why electrons are able to be ejected from a metal. So scientists had to figure it out. Yes.
How could you tell?
I have no earthly idea. You know, I could probably research that this weekend, but I don't want to. Why don't you do that for me?
Extra credit?
Why?
I said it was extra credit.
How
Wait. Does it affect anything? Or does it matter?
For what we need to know? No. I'm just giving you an example of how it works.
Right, you said they go into the atmosphere. Does it affect
It doesn't hurt anything.
So it's just like,
Have they figured it out yet? Like,
so like,
Oh yeah, nothing that I'm telling you is wrong. Now, Bohr's model, which we'll talk about on Monday, Bohr's model they have fixed because part of what he did is wrong. Now, on Monday, I'll correct Bohr's model, and we'll talk about the parts that they figured out about the photoelectric effect. Now, your homework. The homework sheet has two sides. You are doing only down through question number 11. So stop whining. Now, you have 1 through 11. And what do we have on Monday?
yes.
See? Not so bad. I don't know who's little pink paper's on the floor here. Somebody needs that pink paper or what? It looks like it's kind of fancy, right?
Oh, not all of it. I guess it is.
1 through 11.
It's like getting like a unknown voicemail call.